所以上回我们介绍到这个电磁波的 polarization. A key point is that we define the polarization direction of a wave according to the motion of the tip of the electric field. 所以呢，电场的方向就是电磁波的偏正方向。OK， 那So in general, if we decompose the field into two components in the plane perpendicular to the propagation direction, suppose that the wave propagates along z direction, and we decompose the field into two components in x and y. So if these two fields are in phase with each other, say the x component and y components have the same phase. Therefore, the direction of the electric field is fixed along some direction. Then we call this linear polarization. Okay, 线性偏正. And last time I showed you a film on YouTube that for linearly polarized light, the direction of the electric field is fixed along some direction, but the magnitude oscillates with the frequency omega. OK， 你如果定在这个地方的话，然后呢，你量它的这个偏正的讯号，在这个地方，你如果有一个 meter 的话 ，then you're going to measure oscillation of electric field along some direction, but at this frequency. OK， but in general, there could be a phase difference between this component and this component. And the magnitude between these two components could be different as well. Okay, so this is a general case. And so you can deduce that for this general case, the tip of the electric field is going to rotate on an ellipse. 在一个这个椭圆上头呢，它会旋转。这旋转的这个这个频率呢是多大？这旋转的频率也是跟这个欧米伽一样。OK， 每一个周期这个电磁波一个周期它绕一圈。OK，and this angle along the major axis between the major axis and x-axis given by this expression. And I ask you to do it as an exercise. Okay. Well, for the special case that this phi, the phase difference is 90 degrees different from the other component, but this could be positive 90 degree or negative 90 degree, plus or minus 90 degree. And in terms of phasor notation, you have plus minus j in front of these y components. Okay, given this, if you have a j 90 degree difference between this y component and x component, then you can write down an expression like this. This is an upright ellipse, 是一个正椭圆。OK， 你的中间 cross product term 不见了。因为这里变成 cosine 的90度 ，OK， 所以 cross out this term， 所以呢，整个式子变成一个正椭圆。The length of the major axis, or the length of the axis, is going to be proportional to EX0 and EY0. Okay, and for this case, it's very easy to calculate the angle. This alpha angle is now just EY over EX is tangent alpha. So you quickly have this expression. Basically, just have this expression divided by this expression. Okay, y 除以 x 项之后呢，你就得到这么一个项。所以你得到一个 tangent alpha equal to minus plus. EY0 EX0 tangent omega t minus kz term. Well, in fact, there could be some arbitrary phase right here. Okay. 所以你可以看到这个角度 this alpha now is a function of t and z. So it tells you that this angle changes with time and position. And if we have a say plus sign here, 那这个角度呢会随着时间，这是真函数 tangent is a monotonic increase function. So as time increase, if you pick up this plus sign, you expect that the alpha go with time, right? If you pick up this plus sign, if you pick up a minus sign, you expect that the alpha go down with time. 所以呢，这个 alpha 的角度有变大变小的这个状况。Okay, so if you pick up this plus sign, then alpha increases with time. So if you just sit here, and then the wave propagate towards you, 这个波朝着我这地方打过来，我会量到什么？我会量到这个 alpha 呢是往左在旋转，因为 if alpha increases with time, this tip is going to rotate to the left. Okay, 这个 x y 你要注意 when you plot this x y axis, this means that your z axis is along this direction. Okay, so for this plus sign, this alpha is going to rotate to the left. For alpha, if you pick up this minus sign here, this alpha is going to go this clockwise rotation. So this plus 90 degree, minus 90 degree tells you the sense of the rotation of this tip. So sense of rotation 是由这个正负号来决定的。Okay, and somehow we need to give you a name to tell this kind of rotation. If alpha increase with time, rotate counterclockwise direction, then use your right hand, use your thumb, point to the propagation direction of the wave. Then the four fingers will follow the rotation of alpha. Then we call this right hand rotation, right hand polarized wave. 这是右手偏正。Okay, for alpha rotate in the clockwise direction, you have to use your left hand to do this. So if alpha rotate in the clockwise direction, then we call it left hand polarization. Okay, 所以呢是由这个手来决定来描述这个旋转的方向。但是在有些光学的书里头，所以 for this kind of polarization we call right hand polarization, and for this rotation we have left hand polarization. But in some optics book, they remove this hand. So when this hand is removed, 你如果把这个手，这个不用手来定它方向的话呢，如果是从这边旋转的话，对你来讲，你面对它的话，是它转到左边还是右边？是转到左边哦。Okay, so right hand polarization, in fact, in some artist's book, it's going to tell you that this is left polarization. So you remove this hand, you have to change this to left. If you remove this hand, you change this to right. Okay. So the terminology are not so consistent in the textbook. Okay. So, but in this textbook, you stick with this kind of right hand, left hand polarization directions. All right. Well, once you look at this, this expression, you recognize that if this EX0 is equal to EY0, this is a circle, right? So you have a circular polarization. 如果说这个两个值是一样的话 ，EX component, EY component are the same, then you have circular polarization like this. Okay, same thing. This alpha now, you don't have your EY0 divided by EX0 is equal to 1. So your alpha is very simple. This alpha is directly equal to minus plus omega t minus kz. Okay, so this is circular polarization. 那，我们来看一下这个 I got one animation for you. Let me just log in. So there's a 3D animation for the polarization of waves in YouTube. So I dig it out for you. Hopefully you can see 3 polarizations. Well, this one is a linear polarization. You see the electric field vector stay stationary along one direction. And this is the right-hand polarization. This sense of rotation, when you view from this direction, you're going to see that it's rotating according to your right hand rule. Okay, and this is the elliptical polarization. The electric field line, electric field amplitude is sort of uneven when you rotate. So let me do it again. So you can see one more time. 你可以想象这个波从这边跑，从这边跑，然后你在这边看，这是线性偏振，这是圆形偏振，这是 elliptical polarization. Okay, so this is 3D view of the polarization of waves. It's very nice that you can view it 3D and real time, right? So this is the polarization of wave. Well, there are a lot of applications associated with the polarization of waves because you can control the energy of the light by controlling the direction of the polarization, the electric field of the wave. Well, the electric field of a wave, electric field of an electromagnetic wave can interact with materials because electric field can interact with the charges in the material. 在一些物质里头都有带电的电荷，所以呢，电场会拉动这些电荷。But for natural light like this， 像这种这个光的话when we manufacture this light, we did not tell the light to emit with a polarization along a certain direction. So the polarization direction can be any direction. Okay. 那我手中有几片这个 Polaroid polarizer， 这个东西呢有个称呼叫做 Polaroid polarizer。这是有点像塑胶片 ，OK，Polaroid Polaroid is a company name. 在西方国家里头呢，很多的产品是用它的公司的名字命名的。OK，Polaroid，这是什么？拍立得照相机，古时候的那个有个拍立得这个品牌的照相机。OK， 那这个 Polaroid polarizer is there's a polymer, there's some sort of chemical polymer coated on this plastic surface. And this polymer can be easily stretched by the electric field. 就像 if I have some spring, then it's quite easy to stretch in this direction. Okay, and when the electric field of the light stretch the polymer will absorb the light for the polarization along some direction. 因为它很容易被拉动。这里头的这个高分子物质，所以呢，这个光打上来之后呢，只要是偏振在某个特定方向的 component 就被吸收掉。Okay, so there's some transmission axis associated with a piece of Polaroid polarizer, and so if you decompose the light, say the light at one time, at one instance, is polarized along this direction, you can always decompose it into two perpendicular directions. So you can use a piece of polarizer to absorb the polarization along this direction and leave it the polarization along this direction. 所以呢，我如果把这个偏振片呢，拿过来，如果说它的这个穿透轴是在这个方向的话，那在这个偏振片后面的这个polarization 就是在这个方向上头，因为偏振在这个方向上，光都被吸收了。Okay. Now, if I put two polarizer with their transmission axis perpendicular to each other, then the light cannot transmit. So you see a dark spot right here. Okay, because no light can be transmitted through two cross polarizer. If I have two cross polarizers, then you see a dark spot right here. Okay, the light cannot transmit through this cross polarizer and reach your eye. So you see a dark spot. But if I rotate 90 degrees, you can still see me, right? You can still see through this polarizer. By controlling the transmission of the light, you can have some applications. For example, this screen, in fact, has a polarizer on it. This is an LCD screen, and there's a backlight illuminating a film of LCD. And LCD is some element that can control the polarization of the light. Okay, so there are a lot of pixels. 有很多的这个显示点在这个上头。And on this screen, there's a thin film polarizer, very similar to this. Okay. 那如果说你不让这个光出来的话呢，你就把这个后头用 LCD 用电子电路控制这个 LCD to polarize the light so that the light cannot go through this polarizer. Therefore, you see a dark spot on it. 如果是这个暗的话，这表示说光出不来。所以呢，这上头有一片偏振片。Okay. 所以the light transmitted through this screen is polarized. So I can verify by using a piece of polarizer and put it on top of it. Okay, I'll make it brighter. So you can see that if I put a polarizer on it, if the polarization of the light going out from this screen is aligned along the same transmission direction of this polarizer, then you can still see the characters, the display behind it. But if I rotate it to a certain angle, I create a dark spot on it. Basically, I cut out all the light going out from this screen. And if I continue to rotate it, then now I allow the light to go out again. OK， 那这个不同的颜色呢，它前面都有这个polarizer， 然后呢用液晶控制不同颜色的 polarization 的方向。OK， so this is one application about the polarization of electromagnetic wave. Another example is this projector. Same thing. There's a light in the back of this projector, and then the light goes through some LCD elements, and the LCD control the polarization direction of the light. And in front of this projector, there are polarizers. For different color, you have different polarization element to control, to absorb the light or transmit the light. So if I put a polarizer right here, 这个从这里出来的光，它是已经有偏振化的光，而且呢，不同的颜色呢，它偏振在不同方向上。所以呢 ，if you put a polarizer right here, then you see that this is some color behind this polarizer. Okay, and now if I rotate it, you change the color. So different color, in fact, polarized along different direction. Therefore, you can mix the colors to show the different colors on the screen. So this, if I take out this, you can see clear that this is green, but if you rotate it, it becomes purple. OK， 那这个是靠光的偏振来控制你显示的这个颜色，这个也是一样。我这里没有绿色跟紫色，不然的话，你可以看到就是如果说这里是紫色的话，我放上去之后呢，这里会变成全黑色。如果说因为它没有这个绿色的光 ，OK，anyway， 所以这是光的 polarization 的一些应用。我手中带了几片过来，你们可以发下去玩一玩，看一看再还给我。这都是叫做 polar 偏振片。给你，你也可以透过呢偏振片看这个 screen， 你会发现这个有不同的这个效果，而且呢。If we just see through the polarizer and try to see some reflection of the light from the table, in fact, you're going to see that the polarization direction for the light reflected from this table is not symmetry about x and y. 一般来说，这个日光灯下来的光的偏振方向呢是。x 跟 y 的几率是一样的，但是经由反射之后就会不一样的。那这个 hopefully we can go to this point before we finish the lecture in this semester, because when sunlight is illuminated to some surface, for certain polarization is going to be more absorptive, and for certain polarization is more reflective. 所以呢，这个如果有一个表面的话呢，有反射光，这个反射光的偏振态不再是像这个一般的太阳光或者是人造光这么的对称。OK。Okay. We have talked about this plot before. If there's an imaginary plot in the permittivity, then the wave can be attenuated in this material. Okay. 那这个部分呢 we have talked about this in chapter 1 and also in the end of the last chapter, this part is responsible for the absorption of the material. Because of the existence of this term, your K now is a complex number, and then you can write your K this into a term gamma equal to JK, and there's a real part and imaginary part in it. Okay, and then you take a square root of it. This imaginary part tells you the propagation of the wave, and this alpha tells you the attenuation of the wave. And by now you are very familiar with this, right? With this real part and imaginary part, your E and H, the two field, is expressed by this harmonic term multiplied with an attenuating term， 一个消散的这个像在这个地方。那这个波怎么跑呢？当然是由这个来决定。So you have a phase velocity omega over beta, not over k. This is phase velocity is a real quantity. It cannot be imaginary quantity, right? So the phase velocity now is omega over beta, and this alpha tells you how fast the wave attenuates. If we just look at this blue curve, the amplitude drop over distance. Okay, so there's attenuation associated with it, and described by this term exponential minus alpha z. OK， 那这个呢是来自这个epsilon 这一项。Now think about if I have a wave instant on piece of metal or conducting material, a piece of good conductor. Then for the Ampere's law, let me write down the phasor notation. Okay, just phasor notation. This is J omega epsilon E plus J. This is phasor. Okay, 都是 phasor. 我懒得写了，我就这个小帽子我就不再写了。Well, this is equal to sigma E for conducting material. So you can organize this into J omega epsilon plus sigma E, or you can write into J omega epsilon minus J sigma omega E. 之前没有这一项在那个地方 because we deal with vacuum or dielectric material. But with a piece of conductor, the J, the electric field will induce a current on this piece of metal. Okay, so you have to take into account this J. With this J, you end up having this term, and without the current, without J, you only have epsilon. So now you have complex permittivity equal to epsilon minus J sigma omega. Okay, for the wave instant on this piece of conductor. 好，所以现在我们就可以来算一下我们的 K 是什么东西 ，right? This K is equal to JK is equal to J omega mu epsilon complex epsilon. 我们可以继续往下算的话呢，是这一项会等于 J omega square root mu epsilon minus J sigma over omega. 那继续往下算的话是等于 J omega mu epsilon square root multiply with square root 1 minus J sigma epsilon omega. 你的这个 gamma 会算到这个程度来。Well, suppose that this is a very good conductor. Okay, suppose this is a very good conductor. This means that this conductivity can be very, very big. Okay, so let's make an assumption for a good conductor. for a good conductor, let's assume that this is much larger than this one. So your gamma now is equal to alpha plus j beta is equal to j omega square root mu epsilon, and then square root minus j sigma omega epsilon. And this is an approximation. Suppose that you have a sigma epsilon omega much larger than 1. So you can do this. So you have a minus j inside the square root. And so we can continue to solve it. This minus j is equal to exponential minus j pi over 2. So this is, if I write here, this is equal to omega square root mu epsilon. This j is exponential j pi over 2. And for this minus j, this is going to be multiplied with exponential minus j pi over 4. Pi 除以2再开根号变成4分之 pi. And then for the rest is sigma omega over epsilon. Okay. So this is kind of step-by-step derivation. 这项会给你 exponential j pi over 4. This is equal to 1 over square root of 2 minus j 1 over square root of 2. Cosine 4分之 pi, sine 4分之 pi. OK， 所以呢，你这里会变成是1 over square root of 2, 1 plus j, and then this become omega sigma. This cancel each other, and this is mu right here. 变成这个样子。那有时候呢we really don't want this square root of 2, so you write down omega equal to square root of omega equal to 2 pi frequency. Okay, so this square root of 2 cancel with this square root of 2. So you have gamma equal to alpha plus j beta roughly equal to square root pi f sigma mu multiplied with 1 plus j. So immediately you identify that your alpha equal to beta equal to square root pi f sigma mu. Okay, so let's come back to this picture. It tells you that your wave inside a piece of conductor is going to attenuate like this. The blue curve, the amplitude is going to go down as it propagates into this piece of conductor. The attenuation is very quick because this alpha is proportional to square root of your frequency. So for high frequency electromagnetic wave, it cannot penetrate into a piece of conductor, and most of the energy is reflected in the backward direction. Okay, and how fast this amplitude is going to drop like this. All right. This is, say, initially you have E0, and then at some point you have E not divided by E, and this distance we call Z. The distance from here to here is going to be equal to 1 over alpha, because your electric field is equal to E naught multiplied with exponential minus EZ, and then cosine something, right? So for the total amplitude drop to 1 over E, the distance is, the corresponding distance is 1 over alpha. Okay, and we said that this 1 over alpha pi f sigma mu is called skin depth. Okay, this distance is called skin depth. 它的物理意义。来，你这个距离 ，if you look at this term, exponential minus alpha delta is equal to exponential minus 1 over E. So this delta is equal to 1 over alpha. Okay. Any question? 没有 ，right？ 所以这是一个例子，就是你如果把一个电磁波打到一个 good conductor 里头，那它的这个场呢会往下掉，会慢慢的被吸收掉。Well, that is for the electric field, but given an electric field, you can actually calculate the magnetic field, right? For if you know the electric field of a wave, then your magnetic field is equal to 1 over eta, propagation direction crossed with the electric field. This eta, well, in terms of magnitude, if we just consider the magnitude, then this H is equal to E divided by eta. But now your eta is defined to be mu over epsilon. But your epsilon now is a complex number, so let's put C underneath of it. So your wave impedance is also a complex number. Okay. 那在这里呢，for that case, you have mu epsilon C is equal to epsilon minus J sigma over omega. So you can do the same approximation by taking out mu over epsilon, and then you have 1 over 1 minus sigma J omega epsilon. Now, suppose that this term dominates for a good conductor. We have a assumption that this conductivity is very big. So we assume that sigma over omega epsilon is much larger than 1. So I can cross out this term. If I cross out this 1, this minus Ga become plus J right here. Okay, so 根号 J, we have calculated this the square root of minus J right here. Minus J equal to minus J pi over 2, and take a square root of it. So this is going to give you exponential plus J pi over 4. And this is equal to 1 over square root of 2, 1 plus J. 有没有问题? Yep. I go through this one step by step. Hopefully you can follow my calculation. OK, 所以这里可以把它拿开了，这里变成 square root of mu epsilon, and you have 1 over square root of 2, 1 plus J. And then now you have a square root of omega epsilon over sigma. OK， 那一样，你这个 epsilon cancel 掉，你这里呢会变成1 plus j， what square root of sigma pi f mu。OK， 你如果在这里呢，乘上一个 sigma conductivity， 这里变成平方 ，and you recognize that this is alpha over there. This is your alpha right here. OK， 所以呢，你可以把它写成这个呢 ，at c equal to 1 plus j alpha over sigma. Okay. Well, the key point is that it's not this derivation. You can always do the derivation by yourself. The key point is that your wave impedance is a complex number. If this wave impedance is a complex number, then H and E are not going to be in phase. So now your H is equal to E divided by eta, and this is phasor. You calculate this eta equal to 1 plus j, and then alpha over sigma, and then you have electric field. So this means that your magnetic field is equal to the phasor of the electric field divided by alpha over sigma, and then this is equal to exponential j pi over 4. So multiply with the square root of 2. So this is equal to this expression multiplied with exponential minus pi over 4. 所以你发现呢，就是 H field 跟 E field 之间有个相位差，这个相位差是45度角。OK， OK， 有没有问题？有个45度角相位差，所以 if I write this E phasor to be E naught exponential, say minus j beta z plus some phase, and if I convert this into E naught cosine omega t minus beta z plus phi naught. Okay, if I write the electric field like this, how do I write the magnetic field? My magnetic field as a function of time position is going to be equal to E naught, and then divided by this factor, square root of 2 alpha sigma, and then multiply with cosine omega t minus beta z plus phi naught, and then minus pi over 4. Okay, this will be the expression for my magnetic field, because there's a phase shift between E field and H field by 45 degrees. 所以呢，我如果实际上去画它的这个场的话，say if I have an electric field like this, okay, 在 say at z equal to 0, phi 0 equal to 0. Okay, this is t, for example. At t equal to 0, I have this is E0. 但是呢，对于这个 h 来讲的话呢，它是 cosine 的负派除以4，所以呢，我的这个 h 场的最高点是在负派除以4的地方。So if I plot the magnetic field, my maximum point is right at this location. So I have a phase delay. Okay, I have a phase shift between the H field and the E field. 所以 E 场跟 H 场不见得都是在同一个相位上头。Okay, for this particular case, in a piece of metal, there's a phase shift by 45 degrees between the electric field and magnetic field. That is because the complex value of this vacuum impedance. OK, 有没有问题？那下几页呢是告诉你说，如果说这个 epsilon double prime is small compared with epsilon，的时候，它会是怎么样一个状况？那我基本上把它跳过 ，OK， 那个都是你自己可以看的。那一个 real example is that in the conducting material, this epsilon double prime is expressed by this. OK， 你注意到就是，当这个 epsilon 是一个 complex number 的时候呢，for this example, this epsilon double prime is expressed by this for the conductor. But for this case, if we don't spell out what epsilon double prime is, well, usually in the dielectric material, 在介电物质里头呢，这个 epsilon double prime is small compared with the epsilon prime. The imaginary part is usually much less than the real part. Given this, you can do a Taylor expansion to this expression, and then you have this kind of real part and imaginary part. So immediately you can solve for alpha and beta. OK， 那 beta 是它的 propagation， 但是你注意到这个 beta 呢写成这个样子的话，那你的这个 phase velocity 呢会有一项是跟这个这个虚数部分相关的。Okay, and sometimes this beta is a function of it's not linearly proportional to omega. So in some cases, for example, in your textbook, if you send the electromagnetic wave into plasma, this omega is not going to be linearly proportional to omega. So your phase velocity could be a function of the frequency. Okay. 也就不同频率的这个讯号呢，它走的 phase velocity 是不一样的。So if I have plot omega over beta, if you have a linear relationship, this omega over beta is not going to be a function of frequency. But in some cases, you could have this kind of nonlinear curve. For this case, omega over beta is a function of frequency because of this nonlinear behavior. OK， 那你看一下你的这个教科书里头呢，有一个例子，就是你把这个电磁波打进电浆里头去，或者是叫做等离子体里头去，它的 behavior 其实是这个样子。OK， 这里有一个特征的频率，所以看一下你的教科书。I will see you in 10 minutes.